This video is all about conservative vector fields. Let's start with a definition. So we say that a vector field, vector capital F, is conservative if our vector field is actually the gradient of some function f. And if that happens, then this function little f is called the potential of our vector field. Here we have a couple of facts that allow us to quickly check whether a vector field is conservative. So if we have a vector field with two components, the way we check if it's conservative, check if the partial derivative of p with respect to y is equal to the partial derivative of q with respect to x. So a vector field with two components is going to be conservative if and only if this is true, meaning our vector field will be conservative exactly when this condition is true. If our vector field had three components, then that vector field is going to be conservative exactly when the curl of our vector field is equal to the zero vector. In this example, we're going to practice finding a potential for a vector field. So in part A, we're given a vector field. Presumably this vector field is conservative because we're being asked to find a potential for it. But if you wanted to check that it was conservative, just check that the partial derivative of the first component with respect to y is equal to the partial derivative of the second component with respect to x. So that does work out, but in approaching this problem, I would just trust that that was true because we are being asked to find a potential. So here's how we go about finding a potential. We're going to think about this function, little f, which is our potential, in a couple of different ways. We're going to say, on the one hand, it's the integral of the first component of our vector field with respect to x. So let's integrate that with respect to x. We'd have x cubed y to the fourth. And in general, we'd say plus a constant, but really what we mean here is we could have any sort of y terms. Those would all disappear when we take the partial derivative with respect to x. So you could have something like y squared or e to the y or something, and that would disappear when you did the partial derivative with respect to x. And it's also true that our potential, this function little f here, is equal to the integral of 4x cubed y cubed plus 9 with respect to y. So we're going to integrate the second component of our vector field with respect to y, and that's going to give us another piece of information about f. So integrating with respect to y, we'd have x cubed y to the fourth plus 9y. And in general, we could have some x terms here that would have disappeared when we took the partial derivative with respect to y. So you could say something like h of x, that would be the formal way of saying it. Now both of these facts are true, and we're really looking at our function f from two different vantage points. So if we match up the terms in both these expressions, we should be able to get complete information about f. So any mixed terms that involve both x and y will come up in both expressions. Any pure y terms will only come up over here. So we're able to find the value of g of y by looking at the right side here. And we're able to find any x terms by looking over here. Now there are no x terms, so that tells us really our x terms are 0. So h of x is equal to 0 here. So we can write our conclusions down below if we like. So we said g of y was the function 9y, and h of x was the function 0. So with that, we can draw our conclusion. We can say our function f that we're looking for, x cubed y to the fourth plus 9y. So that makes this piece of information true, and that also makes this piece of information true. If you wanted to find all the potentials for our vector field, you could say plus c. But see, since we're just being asked to find a potential for our vector field, I would leave the constant off and just consider the constant to be 0. So this is our potential for our vector field f, and if we wanted to check this, let's just think about the definition here. The whole point of finding a potential is that the gradient of this function little f is supposed to equal our vector field, vector capital F. So you could just do a quick check there that when you take the gradient of this function here, yeah, sure enough, you do get the vector field f that we started with. So that's how we know that we've successfully found a potential. So if someone is asking us to find a potential for this vector field, then that tells us that this vector field must be conservative. But if for some reason we wanted to convince ourselves that it was conservative, you could check that the curl of the vector field is equal to the 0 vector. I would say that's unnecessary, but that's just for the purpose of practicing our definitions here. So the way we're going to find a potential is we're going to think about our potential, little f, in 3 different ways. On the one hand, it's going to be the integral of the first component of our vector field with respect to x. So we'll take yz plus sine y and we'll integrate that with respect to x. That's going to give us xyz plus x sine y. And then there could be some y terms and or some z terms that would have disappeared when we took the partial derivative with respect to x. So the way we'll write that is we'll say g of yz. So that represents y terms, z terms, and anything that's a mixture of y and z. So that's one vantage point on f. We're going to look at 2 more points of view on f, and then we'll be able to put them all together to get complete information. So on the other hand, it's also true that f is the integral of the middle component. So that's xz plus z e to the yz plus x cos y. That integral is with respect to y. Integrating that, we get xyz plus, this term here just integrates to the exponential, e to the yz. You can check when you take the partial derivative of this with respect to y, you do get back to z e to the yz. And then third term here, that's going to be x sine y when we integrate with respect to y. And then there could be some x and or z terms that would have disappeared. So x, let's say h of x comma z to represent those x and or z terms that would disappear when we took the partial with respect to y. And then finally, we'll think about our function little f here from one more point of view. If we look at the third component of our vector field, that's xy plus y e to the yz. Let's integrate that with respect to z. So that's going to give us xyz plus this term here is going to integrate just to the exponential e to the yz. So you can check that when you take the partial of this with respect to z, you get back to y e to the yz. So we did that correctly. And then there would be some x and or some y terms that would have disappeared when we took the partial with respect to z. So you could write something like k of xy to represent those x and or y terms. So the idea of what we just did here is that if this vector field here really does have a potential, then what is sitting in these components are the partial derivatives of that potential. So we can undo that partial differentiation process just by integrating with respect to the appropriate variable. So that gives us 3 points of view now on f. We're going to look at these 3 points of view and put it all together into a single potential function. So here's our answer coming up for our potential. Well, I'm going to circle terms as we use them. So there's definitely going to be an xyz term. There's going to be a term like x sine y. So that comes up here and here. And in the third function, it just appears as the k of xy. So we'll write that down. And let's see what else we've got. We've got this e to the yz. And in the first expression for our function, that just appears as g of yz. So we'll add that on there. And then the only thing we haven't circled so far is this h of xz, and that's just equal to 0. You can think of there being a plus 0 here and a plus 0 here. Whatever this expression is your function involving x and or z. And in this case, there is no term that just involves x and z. So we just get 0 for that h of xz. So we can circle that. We've taken care of that, taken care of everything, and that gives us our potential, xyz plus x sine y plus e to the yz. If you did want to check your answer, the whole point here is that the gradient of this function is supposed to equal our vector field. So we can check that and just confirm that we've done everything correctly. So we've seen how to find potentials for vector fields with either 2 or 3 components. And we've also seen how to check quickly whether a vector field is conservative. Thanks for watching.